In this video, we'll be looking into DIJKSTRA'S algorithm. So before moving on to the algorithm, we should understand what single source shortest path problem is. So this problem involves finding the shortest path from a given source vertex to all the other vertices in the weighted connected graph. So after reducing the shortest path values, they are entered into cost adjacency matrix. So consider this particular directed graph. This particular weighted graph. This is not directed. So if we write the paths here from A to B, it is 2, and from A to C, let me start from A. Okay, A being the single source. From A, I'm finding all the shortest paths to all the other vertices. Okay, so from A to D, if I write from A to D, it will be A to B and B to D. So that is 5. A to B and B to D, that is 5. Next I have A to C. For A to C it is 1, and from A to E, if I write, that is A to C and C to E, that is 5 again. Okay, so this was about the shortest paths. Okay, this shortest path should be represented in cost adjacency matrix. So reducing the cost adjacency matrix, which is of n cross n, we can write, we have A, B, C, D, E, 5 edges. No, so A, B, C, D and E. I'll write 5 edges on this side, and here also I'll write 5 edges. A, B, C, D and E. So yeah, from A to A path exists? No. So one thing, all diagonal values here would be 0, and from A to B it is 2. A to C exists. Yeah, A to C exists, it is direct 1. And A to D exists? No, direct it does not exist. A to E also direct does not exist. B to A not there, B to B not there, B to C is 5, B to D is 3, and B to E is infinity. C to A not there, C to B not there, C to C not there, C to D not there. Sorry, C to D is not there, and C to E is 4 I have here. Next D, D to A not there, D to B is not there, D to C is not there, D to D is not there, and D to E is also not there. Next E to A is not there, E to B is not there, E to C I have, E to C is also not there, E to D is also not. So this method iteratively finds shortest path to the nearest vertex from source and updates the shortest path to the other vertices in the cost adjacency matrix. So the algorithm maintains two sets: the set of vertices for which shortest path has been found, that is the first set, and second we have the priority queue of fringe vertices, that is vertices adjacent to the set. So it repeatedly selects the vertex with smallest tentative distance, adds it to the set of vertices with known shortest path, and updates the distance to its adjacent vertices. So we'll understand this better when we look into the algorithm part. So in textbook we have one algorithm, but then I felt it is complicated, so this was explained in our class. So I have written the same algorithm. So firstly, algorithm NW source and D. What is N here? N is number of vertices, and W is the cost adjacency matrix, where we have I and J. I is for vertex, it will range from vertex I to vertex J. If there is no edge, then the weight is typically set to large value, infinity it is taken. Okay. Then we have source. Source is the starting point which we have to decide, from which we have to decide all the shortest paths. And D value is any array to store the shortest distance. Okay. So we need to compute shortest path from source to destination. Yes. And input is number of vertices, cost adjacency matrix with value n greater than 0. D is equal to, yeah, the explanation they have given. Then D is equal to shortest path from source to all nodes, that is the output. And S is equal to gives the nodes that are visited so far and nodes that aren't. So this was about explaining the role of S. Okay, it keeps a track of nodes. Okay. Then we have for loop. For I is equal to 1 to for I is equal to 0 to n minus 1 do d of I is equal to w of source and I end. So here we are initializing the shortest array to distance d. Okay, for each vertex of I, with distance from the source node to I as given by the adjacency matrix W. Okay, so this means that if there is any direct edge from source I to D, so from source to I, d of I will be the weight of that particular edge. So if there is no edge, d of I will be set to infinity, that we know. Yes, then we are taking S of I is equal to 0. That is, we are initializing the visited set S such that no vertex is marked as visited initially. So if I take S of I is equal to 0, it means that the vertex is unvisited. Then we have end for this, for I am ending S of source is equal to 1. That is, I am adding source to S. So adding the source vertex to visited set by setting S of source is equal to 1. This indicates that the source node has been visited already in the previous for loop. Then again I am taking for I is equal to 1 to n minus 1 do. That is, I am iterating through all vertices except the source vertex. That is why I am taken, I have incremented the value of I here. Okay. So next I have find u and du such that du is minimum. So we need to select unvisited vertex u with smallest tentative distance d of u. So this vertex becomes the next vertex for the upcoming process. So the key part of Dijkstra's algorithm is to choose the next value of u, okay, such that minimum distance value among the unvisited vertex is selected. Okay, next I'm taking for j is equal to 0 to n minus 1. For j is equal to 0 to n minus 1, do again incrementing the j value till n minus 1. Then I am adding u to S, that is, mark the vertex u as visited by adding it to set S. Yes. Then along with that I am adding now we'll look into for loop for j is equal to 0 to n minus 1 do. That is, I am looping through all the vertices of j to find the vertex u. Okay. Then I'm adding u which belongs to v minus s. So ensure that u is a part of set of vertices not in s, that is v minus s I'm taking here, meaning it has not been processed yet, this step. Then I'm adding u to s. So adding u to s is adding the vertex u to set s by marking it as visited. S of u is equal to 1. Okay. Next I have for every v belonging to v minus s do, that is for loop for v is equal to 0 to n minus 1. Here I am looping all the vertices v that are not yet visited. That's why I'm taken v minus s here. This loop checks for each vertex v if a shorter path exists via vertex u. Okay, so that's what this means. Then this part, these two statements are pretty important in this particular algorithm. While writing the program also, you'll consider these two steps only. Okay, so I'll take if d of u plus w of u comma v is less than d of v. This means that if I'm checking if the distance of vertex v through vertex u, okay, vertex v through vertex u, that is d of u plus w of u comma v is less than the current known distance, that is d of u. This is the current known shortest distance which I'm taking. Okay, if this is true, the shortest path has been found. Else I'm updating the shortest distance. Okay, update the shortest distance to vertex v, that is d of v with the new shortest distance found through the vertex u. Then I'm ending if part, for part and for part. So to summarize here, firstly I have initialized the distance of each vertex from the source using the adjacency matrix. Yes, then I'm taking the set of source vertex as visited. Then I'm iterating through all vertices to find the shortest path. Here I'll be finding the unvisited vertex first with smallest distance. Then I'll be updating the shortest path from adjacent vertices, and then I'll be marking them as visited. Then I'll repeat all the processes till I reach this till this condition is satisfied, and finally I'll obtain the d of v value. Okay, so that was about the algorithm part. Writing of the analysis part, here we have input size as n, and the basic operation here is this. This is the comparison operation. If this condition fails, you'll update the d of v value. Yes. Next, finding f of n value. If you look, we have for v, for j and for I, 3 for loops, no? So 3 summations. Innermost I have v, then I have j, and here I have I. I starts from 1, okay, n minus 1. So if I solve this upper limit minus lower limit plus 1, we have discussed this in previous videos. So if I solve this, I would get 2n square minus 2n. So further I can write order of it as order of n square. So, or if here n is the vertices which I have taken, right, so I can write it as theta of v square. So this is the analysis part. It is theta of v square, okay, where v is the vertices. So we have looked into the algorithm part, we have understood the analysis part. Let's quickly solve problems on Dijkstra's algorithm. So starting from the first problem, here they have asked us to find the shortest path using Dijkstra's algorithm. The question is pretty straightforward. We should start solving it. So for this, I need to compute table, okay. So here I'll have the 3 vertices. Here I'll take the remaining vertices. And here I'll have the illustration part. So here I'll take S. Source node is A. So I should start from A. So from A, I don't know the initial distance, so I'm taking it as empty. From A, I'm taking it as empty. From A, I should check all the adjacent nodes. From A to B, I have the distance as 1. Yes. From A to C, I have it as 5. Yes, I'm done with B and C. For D, E, F, it will be infinity because there is no direct connection. So for D, E and F, it will be infinity. This is understood, pretty understood. So among these two, which one is the shortest one? Shortest path, having shortest distance. It is this one. So I can write it as A to B 1. Yeah, I'm done with the first step. Let me draw a line here. I'll have to consider this from A to B with 1. So A to B with 1 I'm taking. Now from B I have to look. But here one change compared to Prims and Kruskal's is that the connection and distance needs to be taken from source vertex A. So while considering source vertex small a, so from B, if I consider from B, it is D and E. So B, D, E, C, 3 edges, 3 vertices are there connected from B. These 3. Let me write for these 3. So from B to D is 2, but A to B is 1. So 2 plus 1, 3 I'll get. Yes. Then I have to D. D I have written. Next I have to C. So B to C I can write it as 2 plus 1, 3 again. And B to E. I can write 1 plus 1, 2. And for F, it is infinity only. This is understood. So among these 3, E to B has the shortest distance, no? So I can consider this. So it will be from A to B 1 and B to E 1. So next, let me draw a line here. I'll consider this from B to E with the distance of 2. Now from E I have to look. From E I have to F. From E I can go to F. And is there any other path from E? No. From E to F, let me write E to F. So it was 2 till here. Again E to F is 2. 2 plus 2 is 4 I have. That is, I've moved from A to B and B to E and E to F here. Next, if I look at the other paths, that other edges, that is C and D, these are not reachable from E, right? But I have to find the minimum distance, the shortest path from source to all the other vertices. In this condition, I'll be considering these previous values from B to D and B to C. So let me write it here. B to C it is 3 and B to D it is 3. So among these two, if I check among these 3, which one has the smallest distance? It is these two. Among these two, let me select this. Okay, so I'll get it as from A to B I went, it is 1. From B to C I went, it is 3. And from B I went to E also, that is 1. So this much we have obtained. A, B, C is done. D is remaining. E is done. F is remaining. So let me draw a line here and consider this. From B to C, 3. Now from C I have to take. From C, E already visited. B already visited, A is the starting point, D and F are remaining. D and F I cannot reach directly. So previous D and F, these two values, I write it again here. So it will be F from E to F 4 and B to D is 3. So among these two I should select this and I'll get it as A to B I got 1 and B to D I got it as 2 and 2 plus 1 3. Yeah, this is okay. B to C is 1, B to C is 2 here. So I'm done with A, B, C, D and E is remaining. No, I'll write E here 1. So I'm done with this. Let me draw a line and write this B to D with distance 3. Now A is done, B is done, A is done, B is done, C done, D done, E done. F is remaining. So to write for F, from D check if F is reachable. Yeah, so I can write from D to F it is 4. That is from A to B I went 1 and from B to D it is 2, 1 plus 2 3 and from D to F it is 1. So 2 plus 1 plus 1 it is 4. Yeah. Next previous value which I have that is D to E is 6. So I need not yeah. So among these two, this has the shortest path. I need not write E actually because E is already visited. So, but then if it is possible to find minimum value, I can, here in this question, it does not signify anything. The 6 is of course larger than 1 plus 1, 2. So I need not consider this. But in general, we should consider the other remaining edges also. Okay. So let me write for this. A to B I went 1. From B to D is 2, from B to C is 2, and from B to E is 1, and from D to F is 1. So this is the shortest, this is the final solution which I have obtained. Here from A I should write all the shortest paths. So here I'll write shortest path from source vertex A and its distances. So from A to B I have it as 1 and from A to C I have it as A to B and C, 2 plus 1 is 3. Next I have A to D, that is 1 plus 2 is 3, and from A to E 1 and 1, 2, and A to F I have 1 plus 2 plus 1, that is 4. So here I have obtained the solution for my question. So this was first question. Let's look into the second question now. So again they have given a particular, this is not directed graph, okay, so this is just weighted graph. So for this I need to find the shortest path. Assume that starting is A. So let me write 3 vertices here. Let me compute the table. Remaining vertices here. Followed by that I have illustration. So I'll start from A. It is empty. So from A I have B and D. So from A if I go to B it is 3 units, and from A if I go to D the weight is 7. So again B and D directly reachable, C and D is infinity. This is understood. So out of these two I'll select B. So from A I went to B. I can write it anyway, okay. I'll write it as 3 here. Illustration part I can write it anyways, because ultimately the shortest path and its distance is what matters in this question, okay, in DIJKSTRA'S algorithm. No, so I'll write it here. From A I went to B with weight 3. Now from B I can reach to C and D. So from B if I go to C, it will be 3 plus 4, 7. And from B if I go to D it will be 3 plus 2, 5. Yeah, so out of these two I can select this, right, having the minimum value. So from A to B I went, that is 3 units previously, and from B to D I went, that is 5 units. Now I'll write this here, B to D 5 units. So here from D I have CE. So from D to C, if I write, it will be 3 plus D to C, 3 plus 2, sorry, here it is 2, 3 plus 2 plus 5, right? So it will be 10. 3 plus 2 plus 5, that is A to B plus B to D plus D to C. D to C. Sorry, this is D to B. Okay, D to C. Yeah. Next, I have from D to E. From D to E, if I write 3 plus 2 plus 4, that is 9 I have. That is 3 plus 2 plus 4. From A to B I went, and from B to D I went, and then D to E I went. Among these two, I should select one. But then previously, if you look here, these two values are also there. Let me write those remaining values also. Here they have A to D as 7 and B to D as 5. So if you consider all these, D is already reached, so I need not consider this. Among these three, I have 7, 9 and 10, D to A. So among these three, this is B to C, sorry, B to C is 7, B to C is 7. So B to C is 7, C is not considered here. So I can take this. D is already considered, no? So I can neglect this. So it will be from A to B I went, B to D I went, and B to C also I can go. A to B is 3, and B to D is 2, and B to C is 4. Done. I should write this now. From B to C I went, it is 7. Now I can write from C. From C I have E. No. So C to E, if I write, it is C to E. So A to B and B to D or B to C. 3 plus 2, 5. 5 plus 5, 10. No. 4 plus 3. A to B, B to C and C to E. Okay. So it will be 13 here. Then writing E to D 9, previous value. So I can consider this. So it will be from A to B and from D to E. D to E I have. So A to B is 3, B to D is 2, D to E is 4, and B to C is 4. So I am done with A, B, C, D, E. All the points are covered here. So even if I write for D to E as 9, here I don't have any adjacent nodes. So this is the final solution which I have obtained. So here I should write shortest path from source vertex A and its distances. So from A to B directly I went, it is 3, and from A to C it is 4 plus 3. It is 3 plus 4, that is 7 I got, and from A to D I got A to D, 3 plus 2. I got 5, and from A to E I got 3 plus 2 plus 4. It is 9. So these are the shortest paths. So I hope you have understood how to solve DIJKSTRA'S algorithm. We have looked into 2 problems. We understood the algorithm and we understood the analysis part also. If you have any doubts, do let me know in the comments and subscribe to my channel. Thank you.